setting up a table like this makes it the easiest approach. So I am going to, I've given T in Celsius and I've given D. I'm going to turn the diffusivity value into the natural log and take the inverse of temperature. So I have at 1,000 degrees, that is equivalent to, or the inverse of that is 7.86 times 10 to the negative 4, and that's an inverse Kelvin. And the natural log of this value for diffusivity is negative 34.6. At 1200, a natural log of diffusivity is negative 31.4, and inverse temperature is 6.79 times 10 to the minus 4. So I could write this equation. I could say natural log of D naught, negative 34.6 is equal to D0, natural log of D0, minus Q over R times inverse temperature 7.86 times 10 to the negative 4. And negative 31.4 is natural log of D0 minus Q over R times 6.79. And that's a set of two equations with two unknowns, so we can just add the two equations, or subtract one equation from the other, which I'll do here. So I have negative 34.6 is equal to natural log of D0 minus Q over 8.31 times 7.86 times 10 to the negative 4. And I've got negative 31.4 as the natural log of D0 minus Q over 8.31 times 6.79 times 10 to the negative 4. So if I just subtract the second equation from the first equation, so I've got negative 34.6 plus negative 31.4, so that's a negative 3.2 on the left side of the equation. Natural log of D0 minus natural log of D0, that gets rid of that unknown. Negative Q over 8.31 times 1.07 times 10 to the negative 4. And now I only have one unknown. So Q then is equal to 3.2 times 8.31 divided by 1.07 times 10 to the negative 4. And that is let's see, that would be 24.9 times 10 to the negative, or sorry, the positive 4. So that's 249,000 joules per mole. Now that I have Q, I can substitute that in either one of my original two equations. I'll use the top one, and I have negative 34.6 is equal to natural log of D0 minus 249,000 over 8.31 times 7.86, 10 to the negative 4. So let's see, 249,000 divided by 8.31 times 7.8 times 10 to the negative 21. Is that right? No, negative 4. Let's try that again. 249,000 divided by 8.31 times 7.8. So I've got negative 34.6 is equal to natural log of D0 minus 2.337 times 10 to the negative 1. All right, I'm getting a different number each time I calculate this. Give me one more chance. Okay, negative 34.6 is natural log of D0 minus 23.4. So move that around to the other side. I have negative 11.2 is natural log of D0. So I take e to the negative 11.2 power. And I get that D0 is 1.37 times 10 to the negative 5 meters squared per second. Okay? 2 equations and 2 unknowns. Let's try on one other example. Here we've got this 2 temperatures, 500 and 700, 2 different diffusivities. And so inverse temperature here is going to be 1.29 times 10 to the negative 3 and 1.02 times 10 to the negative 3, 2.42 times 10 to the negative 12 natural log. This is negative 26.7 and this is negative 24.2. So I have negative 26.7 equals a natural log of D0 minus Q over 8.31 times inverse temperature 1.29 times 10 to the negative 3. And negative 24.2 natural log of D0 minus Q over 8.31 times 1.02 times 10 to the negative 3. And I'm going to subtract the second equation from the first equation. And I get 2.5 negative is equal to negative Q over 8.31 times 0.27 times 10 to the negative 3. So Q is equal to 2.5 times 8.31 divided by 0.27 times 10 to the negative 3. And so I have that Q is roughly 77,000 joule per mole. I'm going to check that. Yep. So with that being Q, I'm going to just substitute into one of these equations. I can say negative 26.7 is the natural log of D naught minus 77,000 over 8.31 times T, that's 773. So natural log of D naught is going to be equal to negative 26.7 plus that 77,000 divided by 8.31 divided by 773. Well, it's 11.99, so we're just going to make it 12.0. So natural log of D naught is equal to negative 14.7 So D0 in this case would be 4.13 times 10 to the negative 7 meters squared per second. Okay, and that last slide is just an extra one in case I needed more space to work example 2. So, this is the end of the third part of lecture 6.